All right, everybody say hi, whoever's watching this recording. They don't care about you. They don't care about you. Okay, so this handout right here and the parent functions, these are separate sheets that go along with section 3.4. And we're going to fill this chart out first and kind of refer to the parent functions. We probably will not get to the notes for section 3.4 yet today. We'll just fill this sheet out, okay? If you want to go ahead and do the homework for this section, or start doing the homework for this section, homework for 3.4 is page, I gotta figure out where I'm at here, page 182, got it. 2 through 22, the evens, and 28 through 34, the evens, and 42 and 46. Okay. With what we do today, by filling that chart out below, you should be able to do all of the 2 through 22, all of those. You should be able to do this entire homework assignment when we fill out this sheet. We will go back through, though, and fill in the notes for 3.4. We'll probably do that tomorrow. But what we're doing in the notes is going to basically be exactly the same thing as filling this sheet of paper out, okay? We're only going to fill out maybe the first 3 columns here, and these first 4, we're going to check those boxes, okay? If you remember this from algebra, you kind of know how this goes. Let's talk about parent functions first, okay? So if you flip over to the back side of your transformation sheet, on the back side of this is this paper, and these are called parent functions. So the first one is a constant function, and he is just a horizontal function. So this would be like y equals 2. Okay, you would really that y equals 2, y equals 7, y equals -3. All of those are going to be horizontal lines at their respective places on the y-axis. So this is y equals -3. Y equals 7 is going to be this line up here, those types of things. Those are all examples of constant functions, okay? They're considered to be constant functions because the x-coordinate is not, or excuse me, the y-coordinate is not changing. It goes through all the way left and right at that same y-coordinate. Y is always equal to 7, or y is always equal to -3. Those are examples of constant functions, okay? The middle one here is called an identity function. I don't call it an identity function. I call it a linear function. Y equals x is the most very basic linear function that you can get. It is a line at a 45-degree angle that goes like this. It is linear. And an example of this, if you put numbers in, would be like y equals 2x minus 3. Okay? How would you graph y equals 2x minus 3? Start at -3, up 2 over 1, right? Up 2 over 1, and that's what he would look like. Okay? So he still looks like y equals x, but he's just altered just a little bit because of the numbers that are in place. Okay? Parent function over here, this is an absolute value function. So y equals the absolute value of x. Absolute value of x looks like a perfect V. Did you know that? Yeah? Maybe? It's kind of coming back to you now. Absolute value of x. He looks like a perfect V. If I put numbers in there, he's moved around or shifted up and down, or maybe he's skinnier, whatever. But all absolute value functions will look like a V of some form. Maybe it's a skinny V, or like a taller one, whatever, moved up, down. Okay, all of them are going to look like V's. Greatest integer function. Have we talked about that in this class? Yes. Okay. We won't talk about him too much. I don't put him on tests at all, because he's just kind of ugly and disgusting. But this was like, if you are 17 years old, you are 17 for the full year until you get to your 18th birthday, and then you bump up to 18 years old. Then you're 18 years old until you get to your 19th birthday. Then you bump up to this 19 spot. That's what he looks like, okay? So won't talk about greatest integer function too much, but that's kind of introducing you to him. Some textbooks will do just one bracket and put the x in there. Some textbooks will do like 2 brackets. I'm pretty sure the calc textbook does 2 brackets. Your textbook does 1, or vice versa. I don't remember which one is which. But anyway, I don't know. It's just kind of the notation. It's kind of like vertex form versus transformation form. I call it vertex form because that's what the calc textbooks call it. Transformation form is what your textbook calls it. I don't know. 2 brackets, yep. So, same, they're meaning the same thing. All right, let's bump over to quadratic functions. These are all parabolas. Okay, your parabola starts at 0, 0. Y equals x squared is his parent function. They call it f of x equals x squared, but those mean the same thing, right? Quadratic. So it might not be just y equals x squared. Maybe it's y equals 3x squared plus 7x minus 2. Okay, that's an example of a quadratic function with all of this stuff in there. But it's just going to move that parabola around and make him skinnier, fatter, taller, shorter. Move him around. Okay. A cubic function kind of looks as though we've taken a parabola and taken this part of the parabola and just flipped it down. So it kind of looks like two halves of a parabola, top and bottom. So it kind of looks like a little squiggle, and the middle part here is 0, 0. Okay, cubic function, y equals x to the third power. If it's more numbers than y equals x to the third power, it will just move him up, down, left, right, tall, skinny, that type of thing. Okay, those are all cubic functions. Okay, you guys don't have this on your sheet, but add it. Y equals x to the fourth power is a quartic function. What does he look like? A W. Okay, we could keep going and do y equals x to the fifth power. What's he look like? Yep, so it's kind of like a cubic function, but with another extra little hump to him. That's a quintic function. Okay, we could do x to the sixth power, x to the seventh power, x to the eighth power. We can keep going on forever. And he's going to kind of do a similar thing, just with an extra hump each time. Okay. Are you ready for the three bottom ones? Okay, I'll wait a second. While we're waiting, Maddie and Caleb, you guys don't have the notes for these like next couple sections. I posted them on Google Classroom. Do you have access to print them off, or would you like me to put them in the office with April, or would you like me to send them home with a sibling if you have a sibling here? How do you want me to do that?
I already printed mine off, so I'm good.
Okay.
Put mine in the office.
Okay, I will have you a packet ready to go in the office.
Okay.
Let me make a note of that. We'll put you a packet in the office. All right, the last three at the bottom. Are we ready for the last three? This is a reciprocal function, y equals 1 over x. He is the boomerangy thing. So we talked about the boomerangy things before. He has vertical asymptote, horizontal asymptote, okay? And they're just kind of like little L's in the corner, okay? The middle one is a square root function, y equals the square root of x. He starts here, and he goes on forever that way. Why does he not go back the other direction? You can't take a negative inside of a square root. So he stops at 0, 0 and doesn't go any to the left. Okay? The cubic root function is the cubic root of x. Y equals the cubic root of x. It's also down here, f of x. Cube root function starts here. He goes forever this way, but he also goes back the other direction. Why does he get to go the other way? You can take the square root of a negative number, like the cubic root of a negative number. You can take the cubic root of like negative 8. What times itself 3 times will give you negative 8? Negative 2, right? So you can take the cubic root of a negative number. That is totally legal. That's why he gets to go back the other direction and the square root does not. Okay, do you guys all remember these functions come flooding back to you? Okay, if you know what these functions look like and you know what these types of transformations over here do to them, you do not have to do any funny business like plotting points or doing crazy stuff. You can just look at the function, say, I know what that looks like, it's moved this way, and plot it and graph it and then be done. Okay? So let's talk about this guy up here. Whoa, I don't know what I just did. Talk about this top guy up here. F of x equals x. This is like y equals x. He is a linear function that looks like this. If I want to vertically translate him 6 units up, what does he look like? Or what will his new equation be? If I want to move him 6 units up, x plus 6, that's his new function. y equals x plus 6. Okay? If I want to move him 5 units down, y equals x minus 5. Okay? A horizontal translation 9 units to the right. What will that look like? It is. So when you're going to the right, put a little star here. I'm going to erase this stuff. Put a little star off to the side of these guys that say, oh, I can't see. Use the opposite sign. So when you're going to the right, you think you're going positive, but it's actually minus. Okay? X minus 9 is what he will look like. And I put him in parentheses. Okay? Which doesn't so much matter. Those parentheses really in this function right here are not doing anything. But it will matter when we go over to the second column. So put him in parentheses. Get used to putting him in parentheses. What will 4 units left look like? X plus 4 in parentheses. That's what he looks like. Okay? All right, let's hop over here, and before we do the remaining ones going down, let's hop over here and do y equals 2x plus 3. If this is my parent function, if that's what I'm starting with, what the equation will look like. So if I'm starting with 2x plus 3 and I move him 6 units up, what will my new function look like? Yeah, it's 2x plus 3 plus another 6, or y equals 2x plus 9, right? You would combine those terms. So that's what he would look like, okay? If you're starting with 2x plus 3 and you move him 5 units down, y equals 2x plus 3 minus 5, so y equals 2x minus 2. Make sense? Okay? Now, 9 units to the right. This one's going to look a little funky, weird. Y equals, how do I do that? You use parentheses, but where do I put the x minus 9? Yes. So instead of him being 2x plus 3, inside where the x was, I put the x minus 9 there. It's not tacked on at the end of the function like the plus 6 and then minus 5 were. Now he is physically inside where that x is. Does that make sense? Okay? So when I do this, I have to distribute the 2 through. This one's going to take a little bit more work. So he will be 2x minus 18 plus 3, or y equals 2x minus 15. Does that make sense? So he will look funny when you start with functions other than just y equals x. Okay, x plus 4, or 4 units to the left, y equals 2 x plus 3, but now the x is x plus 4. I put that inside where the x is. There we go. I'll zoom in a little bit. Distribute the 2 through just like we did at the top. 2x plus 8 plus 3. So y equals 2x plus 11. Is that right? Yeah? Good? Does that make sense? Okay. Should we do one more column over here? The x squared. Y equals x squared. What? Like that? Okay. If we have what? What? Translation means just a shift. Translating it just means you're shifting it up, down, left, or right. A transformation. So these are all transformations. Every single one of these is transformations. But a translation is just shifting up, down, left, right. Okay? So it's not like stretching and compressing. Okay? If I start with y equals x squared and I shift him 6 units up, he would be y equals, I'm going to go through these kind of fast, x squared plus 6. Yeah? 5 units down, y equals x squared minus 5. Okay? What would 9 units right look like if I'm starting with x squared? X minus 9 squared. A lot of people think the square comes after the x, but it's the entire x minus 9 squared. Okay, this guy would be x plus 4 squared. Okay, and we have those 3 columns filled out. The last 3 columns, like x cubed, or the absolute value of x, or the square root of x, those are going to look exactly the same as this x squared column, but with their respective thing done to them. So I don't fill those columns out. Make sense? unless we want to fill those columns out, but you're going to get awfully bored, right? Okay, now the next one, we'll go down and do vertical stretch by a factor of 5. So if I'm stretching vertically, what does a vertical stretch mean, by the way? It's making him taller. What's a vertical compression look like? Making him shorter. Okay, what's a horizontal stretch do? Wider. What's a horizontal compression? Skinnier. Okay, now sometimes making something shorter makes him wider, right? If you take, like we've talked about this before, if you take, like, I don't know, somebody who's tall at the same weight of somebody who's shorter, like if they have the same weight, the shorter person's going to be fatter, right? That's just kind of the way that it works, okay? If you take them and put them in a taffy puller, it's going to make them skinnier, right? Staying the same weight, making them taller is going to make them skinnier, okay? So taller and skinnier go together sometimes as well, right? If you make him taller, you make him skinnier. If you make him shorter, you make him fatter. That's just kind of the way it works. All right, so if I start with y equals x, and that's my parent function, and I vertically stretch him by a factor of 5, what will my new function look like? 5x. Y equals 5x. Vertical compression by a factor of 1/3, y equals 1/3 x. Good? We're just taking that x and multiplying him by 5 or multiplying him by 1/3. Good? Okay, horizontal stretch by a factor of 2. This one involves parentheses. There's an x in there. If I'm stretching it by a factor of 2, though, there's something weird that happens. It's 1/2. So put a little note over here. When we were horizontally translating, we use the opposite sign. Here we use the reciprocal. Okay, so put a little note off to the side that says use the reciprocal. Reciprocal of 2 is 1/2. So that's what he will look like. Y equals, for a horizontal compression by a factor of 1/4, that guy is going to be 4x in parentheses. Okay, let's bump over to the middle column. If we start with y equals 2x plus 3, and we vertically stretch it by 5, I'm just going to multiply the whole thing by 5. 2x plus 3 times 5. So y equals 10x plus 15. Does that make sense? Okay, the next one, the 1/3 times 2x plus 3. What is 2 times 1/3? It's like 2/1 times 1/3. It would just be 2/3. 2/3 x plus, what's 1/3 times 3? This one. 2/3 x plus 1. Okay, now how does it change? How is this a little bit different? Y equals what? The 1/2 x. Think about kind of how we did it up here, where we had these parentheses. You put it in for x. 2 times 1/2 x plus 3. This one is the horizontal stretch. Okay? You're fine. Okay? So I physically put the 1/2 x into the function. I don't multiply the 1/2 out in front. He goes into the function. So the 3 doesn't actually change. 2 times 1/2 x is just 1x plus 3. Right? 2 times 1/2 is 1. So it's just 1x plus 3. Okay, the 4x is physically going inside where the x is. So y equals 8x plus 3. Yep. If you distribute it and you multiply the 2 through, that's what he will look like. Because you use the reciprocal. So the factor was 1/4, so we change it to 4. Yep. This factor is 2, so we change it to 1/2. Okay, the last two down here are reflection over the x-axis. These two are going to involve negatives, but one of them involves inside parentheses, one of them is outside of parentheses. Do you know which one is which? The second one's parentheses. Okay? Really, to this linear function, what's the difference between these two? Those parentheses aren't doing anything, right? If I have a linear function like this, and I reflect it over the x-axis, which does this to it, isn't that the same thing as reflecting it over the y-axis? Yes, but if I start with 2x plus 3, this function, is it going to be the same? No. So a reflection over the x-axis is going to make the whole thing negative, like this. Okay? Which if I rewrite is negative 2x minus 3 versus, what's the last one look like? Just the negative in for the x, right? So that will be y equals negative 2x plus 3. Okay? I'm going to fill in the last column real quick. So this guy will be 5x squared, 1/3 x squared, 1/2 x squared, which is kind of like saying 1/4 x squared. Why are those two things the same thing? I'm going fast, sorry. If I take 1/2 x and I square that, 1/2 squared is 1/4, x squared is just x squared, so it's 1/4 x squared. Does that make sense? If I get rid of him. Okay, y equals, if I plug 4x in there, 4x squared is like saying y equals, what will that look like? 16x squared, right? If I square the 4 and square the x, it's 16x squared. Okay, and then this one, y equals negative x squared, which I can't do anything with, but y equals negative x in parentheses squared. Okay, y equals negative x in parentheses squared. If I take negative, this guy means negative x times negative x. That's what negative x squared means, right? But what is negative x times negative x? Positive x squared, right? So wait a second. If I take an x squared function, which is a parabola, and I reflect it over the y-axis, it becomes the same thing. Yeah, if I reflect it over the y-axis, this part goes there and this part goes there, right? He's going to look exactly the same. If you take the u and you flip it, it's going to look exactly the same. That's why he becomes the same function again. Good? Okay, we'll stop there tomorrow.
Fifth hour class, you will report to
Yeah.
Mr. Arns's room. Mrs. Boniface's fifth hour checkups, report to Mr. Arns.
Tomorrow we'll fill out those 4 columns and we'll do the notes. Okay? Does that sound good? All right, I'm going to quit recording. How are you doing, Maddie and Caleb?
Great.
Good.
Great.